It took Einstein 3 separate eclipses spanning 21 years before scientists lugging all their apparatus could successfully measure light bent around the moon, thereby proving his theory of relativity and landing him his first Nobel Prize. But for me, the eclipse of August 21st, 2017 would conveniently place the band of totality, which is total darkness, directly over my own backyard where fame and fortune awaited. As this was my once-in-a-lifetime shot, it was time to put into action my little scientific experiment dubbed MLSE. My experiment simply had to have an acronym, if nothing more than to create a sense of awe and wonder. My little scientific experiment would hopefully measure the natural radioactive background contribution of our nearest and most powerful cosmic star, the Sun. It's a well-known fact that we live in a radioactive universe where cosmic rays shower down from the heavens above. It's also well documented that the higher you are in elevation, the greater cosmic-induced exposure you receive. Measuring the direct influence of the radiation emanating from the Sun is not as simple as it may seem due to the interference of terrestrial radiation emanating from the radioactive materials that make up our Earth. The combination of varying elevations and different geological structures composed of different mixes of radioactive and non-radioactive material results in a very wide variation of natural radiation backgrounds across the Earth. With the advent of a total eclipse of the Sun, the dense rocky moon should theoretically shield the Sun's cosmic rays, thereby reducing the natural background levels here on Earth. And it's with this simple premise and a $0 budget that the MLSE was born, accompanied by thoughts of stupendous fame and fortune second only to the great Einstein. With about 100 pounds of lead blanket, a lead brick, and a sensitive gamma radiation micro-R meter, I thought it would be easy enough to measure this. The detector available to me was a 2-inch by 2-inch sodium iodide, model GSP2 scintillator type detector, connected via a 30-inch cable to a digital radiation meter model DSM 525. Both the detector and meter are manufactured by W.B. Johnson Instruments. The detector is sensitive to X-ray and gamma energies over a range of 50 keV to 2 MeV and has a nominal sensitivity of 900 counts per minute per micro-R per hour at the 660 keV energy level. Larger sized detectors exist and would have even been better, but I felt fortunate to have this 2-inch version since it was over 5 times more sensitive than the industry standard 1-inch by 1-inch sodium iodide detector. The Model 525 meter has a direct digital readout, making it easy to read the measurements as compared to the older analog-style meters. Another great feature of the 525 was its ability to take 1-minute time counts. Since radiation is random by nature, using the time count feature would help take unbiased and statistically consistent measurements throughout the experiment. When first turned on in my backyard, the meter detector combo read about 2,750 counts per minute background, representing both cosmic and terrestrial radiation combined. When the meter readout switch was flipped from counts per minute to dose rate, it displayed around 3 micro-R per hour, a pretty low level, but we could do better. By wrapping the lead blanket around the detector and positioning a lead brick underneath it while leaving only the top of the detector exposed to the heavens above, the background reading was reduced to about 850 counts per minute. This significant decrease in terrestrial-induced background cannot be assumed to shield out all terrestrial, but it did enhance the detector sensitivity to cosmic radiation. By placing the shielded detector in the forward slope part of a wheelbarrow, I serendipitously got the right viewing angle to the Sun, as well as a convenient way of periodically repositioning the unshielded detector head so it pointed to the Sun as it moved across the sky. With the addition of a clock, small nightlight, and a video recording camera, I was ready for the big event. My measurements began at 10:25 in the morning and ran uninterrupted until 12:30. The total eclipse occurred at 11:33 and lasted just 1 minute and 40 seconds. The radiation meter continuously displayed the average gamma count rate, which was updated once every 2 seconds. A video recorder captured the live readings along with the time from the adjacent clock. During the blackout period, I activated a small light so the meter display was visible and could continue to be captured by the video recorder. Once every 5 minutes throughout the 2-hour experiment, I took a 1-minute timed count and recorded it in my logbook along with the clock time. Other than a missed interval at 10:50, all data were sequential. The graph in the accompanying figure depicts the 5-minute interval readings captured using the consistent 1-minute accumulated average count times. As you can see, there existed a wide fluctuation ranging from a high of about 920 counts per minute to a low just above 750 counts per minute. As the test proceeded, I became discouraged by the fluctuating data and prematurely concluded that the experiment was a failed attempt, but I continued capturing the data anyway. The full eclipse was a magnificent sight to behold, and with safety dark lenses removed, you could see the glorious bluish star-shaped backdrop that surrounded the moon. Many people had come to Idaho Falls to witness this miracle of nature, and nobody I knew left disappointed. It was something I'll never forget. It was simply amazing, and whether my little experiment worked or failed became totally irrelevant against the awe-inspiring event. But it ended all too quickly, and then it was back to the experiment as I watched the moon make its slow but steady departure. After entering the data into Excel, I graphed it and then applied a few different algorithms to see if anything discernible could be lifted from the disappointing, widely scattered numbers I had recorded. Most of the algorithms did not provide anything useful, but then I tried the moving average technique using 6 periods, and what emerged was astounding. The averaging technique, as depicted by the red line in the accompanying graph, showed a clear dip across the elapsed time of the eclipse, with the lowest reading precisely over the full eclipse time between 11:33 and 11:35. Given the data I had collected for 2 days prior to this event, I had estimated the average shielded background to be right around 850 counts per minute, which seemed to correspond nicely with the graph. From the graph, the average full eclipse count rate would be approximately 768 counts per minute, resulting in an 82 count per minute dip from a full sun to a fully eclipsed sun. The 82 count per minute dip, when compared to the unshielded detector measurement of 2750 counts per minute, represents only a 3% reduction during the eclipse. As the unshielded detector configuration is the most common way of measuring natural background, I know that at my elevation of 4,700 feet, the sun's contribution to natural background is approximately 3%. The small contribution by the sun to our natural background was very surprising to me. It seemed only logical that the sun's close proximity with its powerful gravitational and solar influence upon our world would have likewise contributed a significant portion of the cosmic-induced background. Fortunately for us, we're shielded by the Earth's magnetic field that shields us from 99.9% of harmful radiation. Added to that, the atmosphere provides an additional shielding equal to a slab of metal about 3 foot thick. Further study revealed that a Victor Hess performed an experiment not too different from my own during an eclipse in 1912 and discovered similar results. Since then, mankind has recognized the sun's contribution is just one part of the much larger cosmos. We also know that the cosmic rays cover a very broad energy spectrum, some portion of which far surpass the ability of my little detector's ability to see. Victor Hess's experiment would earn him a Nobel Prize in 1936, so it appears that my little scientific experiment was a Nobel-worthy idea, but just about 100 years too late. While fame and fortune slipped by me once again, it was still very thrilling to peer into nature's invisible secrets while simultaneously watching the heavens above giving us a show of a lifetime. From the grandiose interplanetary demonstrations above to the highly structured atomic world beneath us, I am in total awe at the majesty and power that surrounds us. My little scientific experiment may have been insignificant to the world at large, but to me, it gave me an even greater appreciation for the radioactive universe we live in and all the secrets that still remain hidden awaiting our discovery. At Geiger Counter Pro, we make discovering radiation enlightening and exciting.